Today we're going to be talking about the contact modeling in MapleSim. We have recently added a library under the Multibody library in MapleSim called Contacts, and that will be the topic of this presentation. This new library, we thought it would be a good idea to talk about this, to discuss some of the features that are implemented in this library. Hopefully that will help creating new models and adding more features to your dynamic multi-body systems. Before we get to the library and its features and how one could go about creating contact models, I thought it would be a good idea to have a look at the underlying equations, or the way the idea of contact modeling in a 1D modeling environment have been implemented. So I am going to open a model. This model is actually not using the contact library. It is using a equation-based custom component in MapleSim. It is assumed in this webinar that you do have some familiarity with Maple and MapleSim and its features. If you do want to know more about the underlying process of creating models in MapleSim, where we have blocks and components that are connected together to create a multi-body system or a multi-domain system, please refer to our website where you will find tons of material, introduction, and more advanced topics and examples. Here we're going to be focusing on multi-body environment and the contact library only. So here I have a rigid body and two rigid body frame that represents 2 points on this rigid body. I have another rigid body here, and they are connected with this subsystem, which connects to the both end of the top one and also to the other one. This one is a subsystem, is a custom component or custom subsystem that represent the contact forces between a sphere and a cylinder. So a cylinder is modeled with mass and inertia and 2 points on it, and a sphere is modeled with just mass and inertia. And you can see in this case I have mass and also relationships for the inertia written with parametric relationships. Let's have a look at this subsystem. By double clicking, I go inside, and these components, we'll go through them briefly here, will be the way the underlying equations that represent the forces and torques of contact interact with the rest of multi-body systems. We have components that are sensors. These sensors provide information regarding where the cylinder is and where the sphere is. These information are passed to this custom block. The result of the calculation inside the custom block is the force, which is applied to both objects in contact, and also torque, resultant from the force impact from the sphere to the cylinder. This particular model, as we will see shortly its detail, is contact without friction. As such, you can see that the torque is only applied to one side. The torque is not applied to the sphere, as a contact on the sphere without friction will always go through the center of this sphere and will not have any resulting moment. So let's have a look at this custom component. I'm going to double click on this block. Maple custom component template is opened. Here we have modified this DAE custom component template to include additional information that I would want to share with you and walk you through it. Let me zoom in a little bit so that the equations become a little bit more visible over WebEx. So here we are focusing on sphere to cylinder contact. We have 3 points in space. A and B represent the 2 ends of the cylinder, and C represents the center of the sphere. The sphere geometry is represented only by one parameter, and that is the radius of the sphere. The cylinder is has the radius, and the length of it comes from the distance between A and B. So let's go through the steps of dealing with the detection of whether the cylinder is in contact or touching the cylinder or not. First of all, the 3 points in space, A, B, and C. Here in the equation-based approach, we define vectors representing point A and point B and point C in Cartesian space. The sensors that we just saw will provide this information to these equations. We'll see how they all connect together shortly. We would need a vector that goes from A to B. We would need to have a direction for our calculations. So we simply subtract RA minus RB and RA minus RC to get the two vectors. We can use, let me actually execute the lines as I go through. So here we are finding the distance from A to B by using the norm function. This will be the length of the cylinder, and we will use that length to calculate the unit vector EAB by dividing the RAB by the length. To calculate the other one, we would need to find this distance x, which is the distance from A to the projection of point C on the line connecting A to B. This will be the anticipated or predicted contact point depending on the radius of the sphere here and also the radius of the cylinder here. So this distance would be important. Before getting to that, we would need to know where potentially the sphere is going to hit the cylinder. And we do that by projecting the AC onto AB. And we do that with a dot product. So we have that as well. Now that we have x, which is going to be a function of time, because A and B and C move in space with time, we can find the variable vector RAB by multiplying x and EAB, which was the unit vector that we previously calculated. Now, by having that value, we can continue with our calculation. First of all, we can calculate the distance D, which would be by subtracting RAC and RAN and calculating the norm of it. So that is done here. Probably. Let me go back to the beginning and execute all the lines. Maybe I missed something as I was executing. Here we go. Now I need to calculate the inverse of D so that I can normalize this vector, which is the normal vector to the sphere, of course, because it goes through the center of the sphere, and is also normal to the cylinder, which will be the line of contact force. In the absence of friction, the forces will be perpendicular to both surfaces. So I would need the reverse of D. But however, D can become zero. So for those cases that the sphere is aligned with AB, for example, if it's over here, it's not contacting, but nevertheless, the value D, the distance, can be zero. I need to safeguard against division by zero. I'll do that by defining a piecewise as shown here. So if the distance turned out to be bigger than a very small value, I'll just use its inverse. But if it's smaller than that, for protecting against division by zero, I'll just keep the 1 over that small value. So this way I will avoid having singularity. I can have a look at this function here as I'm building the custom component by plotting 1 over D and the capped 1 over D. So the blue line here, you can see that as the value of D becomes smaller than the set epsilon value, it will just keep that value and don't go to infinity. We can continue on with our calculation by finding the vector from the projected contact point, point C, which is the center of the sphere. Now that we have this inverse of distance, we can calculate the unit vector. And the next step would be to find out whether this projected contact point is actually on the cylinder. If we go back up here, this x could be bigger than length in a positive sense, like x greater than L, or x can be negative, which means I'm off on the A side. If greater than L, I'm off from the B side. So I need to know whether I'm on target. So I define that piecewise here. Point N must be between A and B. So this piecewise says you are on target 1 if you are in between, and you're off target 0 if you're outside this range. And I multiplied this B by the calculated contact forces. So whenever I am off target, automatically the forces go to 0 and no interaction between the cylinder and the sphere will happen. Next, I need to write the actual contact equations. Here I am saying if the distance is less than a preset value, L0 is the distance that if the center of a sphere distance to the axis of cylinder is smaller than, then the contact will happen. If it's bigger, the contact will not happen. Obviously, in this case, L0 will be the sum of the radius of the cylinder and the radius of the sphere for an outside the sphere cylinder contact. And here we have basically a penalty type function of spring rate and damping rate, and we make sure with this maximum here that when the two surfaces, first of all, when they reach each other, they start the application of forces at 0 force, and when they leave each other, there won't be any stiction or negative contact force. Then I define the vector for the force. I have the unit vector, I have the value of the force here, and I have the B, which is a Boolean that can be 1 and 0. If I multiply them all together, I will have the vector for the contact forces. When I want to apply the force, I technically have to apply the force. If I go back to one of these pictures, I need to apply the force of contact here for the cylinder and here for the sphere. Sphere is no problem because I know where it is. It's at point C. But the point N will vary along AB. And it will be much easier if instead of applying the force at point N, I use parallel axis theorem and apply the force at A, but compensate with the resultant required moment. So this is where the extra moment term comes from. Going back to our force calculation, here we see that we do a cross product with the moment arm and the force, and we keep that to be applied to the either side, to the appropriate side in the two contacting pairs. As we were going through this equation, I had this yellow lines that will say this equation I want, this equation I want. Those are the equations that I need to put together here as my equation set for my custom components. If you have worked or seen the equation-based custom component, usually this is where we begin. But in this case, we had to do some derivation to get to our equations before we put it in this EQ variable and have the rest of the custom component equation access it. By hitting the refresh all, those equations are evaluated, and I can get the various lists of what I have available to me. Let me actually execute this. So I have the length, which I will set in MapleSim later on to the sum of cylinder radius and sphere radius. I have the damping, and I have this stiffness, and I have that epsilon variable, epsilon parameter that I need to put in there with a small value to avoid division by 0. Once that is done, I can go and define my ports. So these ports, as we will see shortly, this is where the position of the 3 points in space that I need come in. You can see by clicking on this, the type is real signal, the dimension is 3, and with the name, and I have selected the 3 components for the A position that I have defined at the top of this worksheet. The same goes for B and C. The results of those calculations are F and M, which are output signals from this block, and the same variables that we have defined are associated with M, and for F accordingly. Once we have done that, we're actually going to use the default icon, hit the generate MapleSim component, and end up here with this custom block. The sensors set to measure things in inertial coordinate frame or global coordinate frame provide the position of the 3 points, the point A, point B, and point C. They are fed to this block we just created, and the resulting force and torque, and then applied back. This becomes our contact component. Similar approach is used for the contact library. The contact library does actually have a cylinder to sphere contact element that we will discuss shortly. Let's just run this model and see the behavior or the results of the simulation. Here I have the sphere and cylinder floating in space under no gravity, and I am giving the sphere a velocity to go upwards, and it's offset with respect to the axis. See the result from another angle. So going back to the contact library, the contact library consists of elements which define geometry. You notice that in this custom component we had to explicitly define the geometry. What is a cylinder? It's a length and a radius, and orientation. What is a sphere? Is a point and a radius, no orientation. And so information such as that required to be provided to the contact calculation. So each of these elements, and we will show some examples of how they can be used, provide the geometric information, where they are, how they are oriented, and what are the parameters that define their extent. We have already seen the sphere, and we will see again radius. For a rectangle, it will be A and B, the 2 sides, and also thickness. For a disc, thickness and radius, cylinder, length and radius, and for cone, length and the 2 radii of either side. Torus, big radius and the small radius. Again, orientation is also important. Depending on what element is being used, you would select the appropriate contact force component. Unlike the simple example that we just gone through, these contact elements will also include friction between the 2 surfaces, and we will see what other details they can provide to enhance modeling. A contact model will include a number of parameters, and this contact parameter block, it would be a way to organize your model and have a reference place for contact properties. So let's first of all have a look at the contact library version of the model we just created. Let me open that comparison model that I have, which is basically this model and the counterpart of it from the contact library. So the same mass and geometry on either side. I have added an element for sphere. This one brings visualization with it as well. The same sphere radius I'm using here. For the cylinder, this one provides the geometry, and again the length of this cylinder comes from the calculated distance between the 2 endpoints that the cylinder element is connected to. If I zoom in, you will notice that the contact library uses custom or special ports between different objects. These spherical ports are meant to be used between spherical elements and spherical supporting force components. So these are connected together. These ones are representing the cylinder information. So the cylinder information, position, orientation, velocity, angular speed, are all provided through this linkage, this connection to the contact force element, the same for sphere. And all the calculated forces, as we just saw, are passed through the same contact, same connection. It's a two-way connection back to the cylinder, which is then applied through the multi-body connection point to our physical representation of the mass and inertia of the cylinder. You can run these two models side by side, and basically they have exact same representation. We have not activated friction on the contact library version, which makes it identical to the one that we just gone through with direct access to the equations. Identical results from the two models. So hopefully this just gave you a glimpse into how the whole idea of creating this contact library in MapleSim came about. The contact library is, as I mentioned, is limited to primitives, these shapes here. And these shapes can be adapted to a variety of different cases that you can use to represent maybe a simplified version of your more complex geometries that one would encounter in modeling complex dynamic systems. Okay, so let's look at some of the features. Let me just take a moment and point to a few features in this contact library. I am going to drag in one of the contact elements, and we will have a look at the options available. So this one is a cylinder to cylinder contact, and almost all the contact elements that you will find in the contact library will have similar options as this one. For example, in the cylinder under settings, we have an active parameters or pull down menu. By default, it's always active, but you do have option to control when the contact comes into effect. You might have a simulation that the two eventually contacting bodies start to be on top of each other or inside each other. As your simulation moves on and gets the configuration that it needs to be in, then you can activate the contacts from that point on to have access. Or you want to have a door that basically disappears to material to move and then reappears to hold additional material moving through it. So for example, if I select a start-stop times, then I have the option of having a start time. So from this time, if I provide it at 4 seconds, this contact becomes active till the end of the simulation time. I can provide a stop time at a certain time in simulation. This contact will go away and will provide zero force. Or I can have both of them together, as this contact will only be available or act on bodies it is connected to from 4 seconds to 6 seconds in the simulation time. If this is too restrictive and you actually want to make decision about when the contacts comes on or goes off, you can have a Boolean signal. As you know, the Boolean signal gets values from the libraries in MapleSim, the Boolean ones or relational ones, that you can connect them, and based on decision that you make elsewhere in your model, you can control whether the contacts are active or not. The contact modeling, you may choose different formulation. The default would be the one that used for most cases, unless other circumstances make you select other types of formulation. The linear spring and limited damper is similar to what we have seen inside that equation-based custom component. It has provisions to make sure there is no stiction, and when the two surfaces touch each other or come into contact, the force starts from zero, which requires additional nonlinearity being put in there. You can remove that and have linear spring and damper. This would be just for, I would think, just for testing to see what are the effect of it. If someone wants to have the pure linear spring and damper, they can choose to do so. However, that would not be the best choice in most cases. If you do have information about the type of contact, the Hertz type contact can be applied, where in addition to having a linear spring rate or a damping constant, you do have a full nonlinear relationship with exponents for the displacement and also exponents for velocity term in your contact. Addition to that, there is a coefficient for surface friction and another coefficient for smoothness. We use a smoothed friction in contact in the contact library. It uses a tan function, a hyperbolic tangent function, to smooth the friction as it goes through a velocity, relative sliding velocity reversal. The other options that worth mentioning here, in many cases you would want an object to contact another object more than one object. So if you have this side contacting multiple cylinder, or this torus contacting multiple circular surfaces, you would need to put multiple contact and make sure all the contacts or the connection lines are done properly. You can alternatively and more conveniently specify how many contacts you will have at each side. For example, I'm saying that this cylinder contact would have 4 cylinders connected to this side. You can see that the vector port 1 is now vectorized to 4, and 5 cylinder on this side. The utility of that is for these 4, you can ask to be automatically included contact between them. So you can have 4 contacting 5, all combinations. On top of that, you can have those 4 contacting each other, and the same for the 5. So this way you can organize with one component what contacts what, if they are all cylinders. If they're not, depending on the availability of the type of contact, for example, here I can have 5 tori connect or contact a disk, and I have this option to use torus to torus contact between those 5. But if I do it the other way, I won't get any additional option because we don't have disk to disk contact. One would create disk to disk contact through edges by having torus contact, and to sides by using torus disk contact. So it would be a made up component or a custom subsystem that you can create to provide a disk to disk contact. Okay. So this is some of the information here. One more thing before we move on, and that is the contact properties. Another option in the contact is use record. And so right now I am inputting the contact properties right here in the component, and each component can have its own contact properties. Another way that some might find convenient is to use the record. By clicking that, those properties go away, and you get these contact properties. By dragging a contact property block, you'll have access to the parameters for the contact, including the formulation. And you may have multiple contact definition points, so it will organize on top level different types of contact that you might have. And then inside each contact that you have activated record, you will have to put the appropriate name of that record. For example, here I'm using CP1 for this torus contact, which is this one, and for this torus disk contact I'm using CP2, or I can use the same for everywhere, for all contacts. So this will also provide some flexibility in putting together your model in a more convenient way. Okay, so let's have a look at some of the examples. If you do have access to MapleSim 2016, I would encourage you to visit the examples in the that come with the installation of your MapleSim. So under examples, physical domain, you can go to Multibody and you will find 3 examples that are inside the already long list of examples. This one is the tippy top, which is some interesting toy with some interesting dynamics. It was a test basically for us to make sure that our contact library can capture that type of dynamics. So it's a cool example, very simple one, with not so intuitive dynamic behavior. The other one is a climbing robot that this is what you see once you open that modeling from the example palette. It uses the Multibody library and joints, and inside these custom blocks you will see that we have cylinder contact and cylinders. So we are using the contact library to create a climbing robot, a very simplified approach to give you a starting point into how the various components go together and how one can build components. So let's just wait for the simulation to finish. We'll go through the animations and then look at a couple of other examples, not from the example palette. We'll leave those to you to explore on your own. And hopefully these extra examples that I'm showing will eventually be added to the model gallery. But if in the meantime you would want to have access to them, please contact us and we will provide them to you. So let's have a look at the animation if you haven't already seen this. So with a timed signal, the 2 clutches open and close, and the torso extend and contract, and provide a stepwise climbing of this robot grappling 2 columns under the force of gravity as well. Okay, let's get back to the last remaining examples. Here I have one of the other features I want to highlight that in the contact library. Let's have a look at this simple example that uses 3 different contacts all in one place. Here we have a torus, a sphere, and a rectangle. We have torus sphere contact, we have sphere rectangle contact, and we have torus sphere contact. You can see that these acausal ports can be connected together, and all the required information are passed on and forces are applied correctly or summed together correctly. That's so let's just run the animation. I am bouncing a ball towards the torus that is laying flat on the ground, hits the side of it, makes the torus move a little bit, and then reflected back until it falls off the edge of the rectangle. So now let's see what else we can do with this model to make it a bit more interesting. Rectangle has a special feature not shared in other components in the library, and that is you can provide surface velocity. So it by default has 0 surface velocity. It has a normal vector that you can select to orient it in space at the point that is connected. But the other 2 axes that remain you can use to provide velocities, a constant velocity or a variable velocity. If you want to use a variable velocity, you select check this box, use surface velocity input. An input appears on the block, and you would need to provide 2 inputs because it's a 2D surface that we are providing input on. So let's just have it go through 2 sinusoidal motion the two perpendicular axes with a 90-degree phase shift, which basically creates a circular motion of the surface. The actual rectangle does not move, but its surface will have virtually a speed, which, since all of these work with calculating relative contact sliding velocities, everything that comes into contact with this rectangle will feel that that speed and act or react to it accordingly. So here basically is the same model, dropping the ball with at the same location with the same velocity. However, you can see that the torus is going round and round by just the friction force that is applied to the surface velocity. And this time we successfully managed to put the sphere in the middle of the torus. So this type of feature can be potentially used in examples such as the one I'm showing now, and create a simplified representation of conveyors. While we're running the model, this is put together in subsystems, and I can look at each subsystem. Here I'm interested in the conveyor subsystem, which I have here, and basically it's the geometry, a rectangle with a surface velocity in one direction. We want this the objects to move along the direction of the conveyor. And so there's no actual surface being physically moved. It's just object that falls onto the conveyor move the way you would want if so it's still a simplified representation of conveyor, but it can be used to emulate the behavior as the product gets transferred from one to another. Okay, we're done with the simulation and waiting for the visualization to pop up. There we go. Let me run this animation. So it drops from one to another and then continues on its way. We run this again. So there's multiple contacts are involved in modeling such a system. If you're interested, let us know. We can discuss this model in a bit more detail. I will have one last model to show in this presentation, and that would be using the same contact library to create simplified vehicle models. In this case, a mobile robot, for those who are interested in simplified dynamics for robotics. Here I have three torus components. These come into contact with my ground through the torus to ground contact. And these torus components basically represent the wheels of my mobile robot, three-wheeled mobile robot. Let's run this model while we discussing it. Each wheel has two actuated degree of freedom. One controls the speed of rotation. So I have individual control over how fast each wheel is going to be rotated by the controller. And also its orientation can be controlled. So I can have an omnidirectional mobile robot interacting with the environment. I actually want to put environment around it. So I have extra walls created using additional rectangle element, and they all are contact the shield around the robot with one contact, which has one torus at one side and four rectangle on the other side. Makes it a bit more convenient creating multiple contact, as I mentioned before. So this way I can measure the force of contact and send a signal to the controller and say, you have hit a wall, please adjust cord accordingly. Let's have a look at the results. So this is very basic, very simplified, but I'm hoping that it will give you some ideas as how this contact library with the multibody system can be put together to create a bit more interesting models. So I'm going to speed up the animations. We're hitting the wall, pulls back, changes orientation, and continues, hits another wall, pulls back, and selects another orientation. So this one is actually not smart. It's every time that it hits a wall, it reverses velocity for a short time, and then rotates for a short time, and then continues again. But you can imagine a bit more logic and smarts can be incorporated. So if this was actual maze, for example, it could try to map it or find its way out of it. So with that, I am concluding my remarks. Please visit our website and contact us if you had any question regarding contact library in particular, or MapleSim dynamic modeling in general. We'll be happy to assist you and help you with creating the models that you're looking for. Well, thank you very much.